In example number 8, we're going to try to go ahead and take a look at how would we find the derivative for the inverse secant function. Now, fortunately, the technique here is going to be relatively the same as what we just did in the last video for finding the derivative of the inverse sine function. Let's jump right in here. So we can start off by saying, and I'll switch colors back here again, that if it's the case that y is equal to the inverse secant of x, then this means, of course, that the regular secant of y should be equal to x. But of course, y comes from a particular restricted range. Y has to be an angle either from 0 to pi over 2 or from pi over 2 to pi. Now, in terms of the unit circle, that means that I'm going to be working with, very specifically, only kind of the top half of my unit circle right now, excluding all the way up here at the very top where the angle of pi over 2 would be pointing me. All right, so let's go ahead and use implicit differentiation then, just like we did before, to take the derivative of this form of the function, and then I can go ahead and see what result I come up with. So I'll state here that we will use implicit differentiation to obtain, and let's actually crunch it out. So we're going to do d dx of the secant of y, and then we're going to take the derivative with respect to x of just x. Okay, so I have to remember what the derivative of the secant of stuff is. Well, you might recall that's going to be secant stuff, tangent stuff. And then, by the chain rule, I'd have to say multiplied by the derivative of the stuff. That's just going to end up dy dx. On the other side, again, I'm just going to get the value of 1. And so it seems pretty easy here again to get dy dx all by itself. I'm going to end up with here 1 over secant of y tangent of y. And so we're pretty much done here, right? I mean, we found a derivative. That's great. But much like we said in the last video, we would like to get this in terms of x. We want to get this derivative in terms of x. So what we're going to need to do is to be able to get rid of the secant of y and get rid of the tangent of y, so we only have things with x in there. Now, one of these things is really easy to grab right away. Notice that we already are told that the secant of y is equal to x. So that replacement is actually going to be really, really easy to do. This will be 1 over x times tangent y. So we need to get rid of the tangent of y. Now, you may recall there are some trig identities that involve tangents. And if you don't happen to recall what they are, please keep in mind the following. I'm going to go ahead and write some important identities up here. Remember that we have this particular identity, our most famous identity from trig class, sine squared plus cosine squared is equal to 1. And this is, again, really the primary one that you need to make sure that you have dedicated to memory. Because if you know this one, you can actually generate many of the other identities that you need. Notice what would happen if I went through here and I divided each individual term, that is, I divided each side, by sine squared. Well, if I did that here, this would turn into a 1. If I do cosine squared over sine squared, that's a cotangent squared. And 1 over sine squared would be cosecant squared. And you might recall this is another identity. So it's another one that I can form really easily from the first one, just by dividing everything through by a sine squared. Now, if I'm interested in getting something with a tangent squared, I could divide everything by cosine squared, because then I would get sine squared over cosine squared would create a tangent squared of theta. Cosine squared over a cosine squared would make a 1. And 1 over a cosine squared would make a secant squared of theta. So I'm actually going to make use of this last identity here to help replace this tangent of y. So I'll say that we know that the tangent squared of y plus 1 is actually equal to the secant squared of y. Of course, I could rewrite this to say that the tangent squared of y is equal to the secant squared of y minus 1. And if I square root both sides, I can get tangent of y is equal to plus or minus the square root of the secant squared of y minus 1. Okay, so I have this. I have something now to replace the tangent with, except for the fact that, this has plus or minus on it. So I'm going to need to try to figure out if this thing is going to be positive or if it's going to be negative. So let's see what we end up with here. Okay, I can start off by saying that, again, since y is an angle that occurs from 0 to pi over 2, or from pi over 2 to pi, then we can start to make some determinations about what's going to happen with this tangent y. Okay, first off, we can see here that if it's the case that y specifically falls in this kind of first portion, in this first quadrant portion, from 0 to pi over 2, then it would be the case that the secant of the secant of y is actually going to end up, again, on this portion of the picture. If I look at those points, the secant here would end up positive, because the secant is going to represent 1 over the cosine value. And if the cosine value is positive, then the secant value is positive. Now, of course, I can also see here that the tangent of y over here, the tangent, remember, is my y-coordinate of these points divided by their x-coordinates, right? So I'm going to end up over here with, again, still a value that's going to be positive, since both the x and the y values here are positive. So if I'm in this particular region, if I'm over here in quadrant 1, then I'm going to have the secant and the tangent both coming out as positive. Okay, so that's great. Well, I can then see, though, that if it's the case that y happens to be in the range from pi over 2 to pi, that is, if I'm in the second quadrant over here, then the secant of y is actually going to end up being a negative value, right? I mean, it's going to end up being negative. And also over there, my tangent of y, since it's going to be dealing with points in this quadrant, I'm going to take y's, which are positive, divided by the x's, which are negative. I'm going to end up with the tangent being negative. Now, if I take a look at this, I'll see that in both cases, I'm going to end up with this total derivative, or at least the denominator I can focus on, is going to result in a positive amount each time. The secant of y times the tangent of y, if they're both positive, creates a positive denominator. If I'm over here and the secant is negative and the tangent is negative, I'm going to create a positive denominator every single time. So here's kind of the issue. I have to be careful here about how I'm going to make certain replacements. Because if I take tangent and I make it always positive, that's not actually true. I also can't make the tangent always negative. That's not true. So what do I really replace the tangent with? Well, here's what I'm going to do. I'm going to go ahead and state the following. I know that I have this right here, secant y, tangent y, and I know that if I wanted to, I could replace tangent of y with, let's just say I replace it with this positive version here. It's positive secant squared minus 1. Okay? Now, of course, if this piece is always positive, I'm going to need this piece to always be positive. And we know that this piece here is the same as just the value of x. So I'm going to go ahead and replace that as well. The only issue is right now is that x is not guaranteed to always be positive, because if I choose a value in the first quadrant, my x is positive, and if I choose a value over here, my x is going to be negative. So to ensure that the denominator always results in a positive amount, I'm going to go ahead and absolute value that x. Now, I still don't have everything here in terms of x, but again, since secant and x are the same thing, I can go ahead and make one final replacement here. I can go ahead and replace secant of y with x, and since the secant was being squared, my x is being squared. And now I actually have a derivative formula. So my derivative of the inverse secant function is going to actually just be, just write that, inverse secant function is going to be 1 over absolute value of x times the square root of x squared minus 1. So I kind of end up here with a little bit more of a complicated argument. I really had to be careful here to think about if that denominator of that fraction was going to be a positive or negative result. And that can be a little bit confusing to go through at first. Now, don't worry. These are not arguments that I'm going to be asking you to reproduce. However, I do think that it's a good idea for you to understand where these ideas come from, because if you ever happen to forget a derivative of something like this, being able to reconstruct it is very useful. It's also helpful if you understand the construction to be able to dedicate these more easily to memory. We can remember that with the inverse secant, there was difficulty with getting the denominator to be the right sign, and so we had absolute value bars inserted. We can also see over here that we ended up with like a secant squared minus 1. That's how I know I have this form, because it came from this particular identity structure. So those are at least just some tips that I have to help try to remember these identities a bit more clearly. We'll take a look at some more of these inverse trig derivatives in the next video.